And where was this last studies? Yeah.
Five kids.
Really?
4 sons and a daughter.
You just stress them out.
Yes, I'm
Yeah.
really well into it.
It's one of those jobs that you definitely spend the whole 3 hours, and like, I'd rather not pay more.
Yeah,
That's not really a break.
No, I wish we didn't.
We probably got somewhere though.
You don't know, which. I don't know what I gotta go.
So we have the homework assignment from chapter 24 is due on Friday. So let's try to keep it that way so we not to have an assignment due for the weekend and for the spring break. And the plan is to finish with chapter 24 today and maybe a little bit on Friday. And on Friday, we're going to start chapter 25, which is the first chapter from optics. The midterm is going to be graded by Friday, and you're going to have hopefully all midterms ready to return by Friday. So far, from what I have seen, people did quite well on this midterm. So let's hope that when we finish grading and calculate the averages, it's going to look even better. Let's hope for this. And let's start preparing for the last midterm, which is going to be on chapters 24, 25, and 26. So it is going to include electromagnetic waves, and the 2 chapters are 2 optics chapters. Okay, did you look at the homework questions from chapter 24? Any reasoning about it? So, chapter 24, the bulk of the chapter is Introduction to Electromagnetic Waves.
Chapter 14, 16, 19, and 20 problems.
So here on the internet, they're asking for problems 16, 19,
And 20.
and 20. Well, all those 3 problems are from probably from polarization, from the section on polarization. So we probably have to we may have to solve those questions on Friday, but let's see how far we're going to go. So, look, we started talking about electromagnetic waves, and the important part related with electromagnetic waves itself is contained in the diagram representing a standard electromagnetic wave. And the diagram looks like this. you have the direction of propagation of the wave, and you have the pattern of electric field like this. So this pattern is the envelope of the electric field vectors. So electric field vectors are like this. Yes, and so on. So let's not draw all of it. And of course, in direction perpendicular to this direction of oscillations of electric field vector, you have the direction of oscillations of the magnetic field vector. So the yellow is the envelope of the magnetic fields. So like this. And so on. So in other words, the white is electric field vectors. Yes. With amplitude, the amplitude is right here. RMS value is amplitude divided by square root of 2. And magnetic field is the yellow, like this, again, with amplitude of the magnetic field and RMS value of the magnetic field. So notice that the electric and magnetic fields oscillate in sync. So when the magnetic field has maximum value, the electric field also has maximum value. When the electric field is 0, the magnetic field is also 0. So they oscillate in sync. Notice also that the electric field vector is always perpendicular to the magnetic field vector in this standard electromagnetic wave. Also, if this is the direction of the velocity vector, well, the velocity of electromagnetic wave propagation in vacuum or in air is the speed of light 3 times 10 to the 8 meters per second. Right. This is the magnitude of velocity. 3 times 10 to the 8 meters per second. And the electric field is perpendicular to the velocity vector. The magnetic field is also perpendicular to the velocity vector. So you have 3 perpendicular vectors: electric field, magnetic field, and velocity. So this pattern of electric and magnetic field variations moves, in this case, to the right with the speed of light. And our point in previous classes was that this pattern of electric and magnetic field is naturally generated by AC power supply, with terminals of the power supply oriented the way it is shown like here. So the terminals, those wires of the terminals are parallel to the electric field and perpendicular to the magnetic field and the direction of propagation of the pattern. And of course, once you have this electromagnetic wave, the question is how to detect it. And the answer is just use a standard RCL circuit with resonant frequency tuned exactly to the frequency of this electromagnetic wave. So what is the frequency of this electromagnetic wave? Well, looking at the diagram, this length here is the wavelength of the electromagnetic wave. After this length, the pattern repeats itself again and again and again. So this is the wavelength, and the wavelength is connected with the period of oscillations and the frequency the following way. The wavelength is the speed of propagation of the light of the electromagnetic wave multiplied by the period, or wavelength also is the speed of propagation divided by frequency, because the period is the inverse of frequency. So, in other words, the frequency of the electromagnetic wave is wavelength divided by, so from here, the frequency is equal to speed of light divided by the wavelength. So this is the frequency, easily calculable once you have the wavelength, for example. Now, once you have this electromagnetic wave, for practical applications, it is important to know how to detect it. And in previous classes, we said that you detect it with RCL circuits like this. Well, if you want to have the best detection of the electric part of the electromagnetic wave, you better have an antenna that is a wire oriented along the direction of oscillations of the electric field. Because a wire oriented this way is going to create maximum current flowing back and forth in this particular wire. So you need antenna that is oriented this way for the electric part of the electromagnetic wave. Yes.
Is the T in the equation representing Tesla for the magnetic?
So T here is a period of oscillations measured in seconds. So it is how much time does it take to have one complete cycle from here to here. This is okay. Okay, so this is the electromagnetic, the antenna sensitive to the electric part, just this wire. For the antenna sensitive to the magnetic part, you need a loop, circular or any other shape, but oriented in such a way that the magnetic field vector creates maximum flux. And here is the magnetic field vector is the yellow vector, it is perpendicular, and you are going to have maximum flux if the loop is on the plane of the board for the wave that is shown on the board. Well, again, instead of circular shape, you can use any other shape, but it has to be oriented. The loop has to be on the plane of the board. So if you use, let's say, rectangular shape, you just have to have a rectangle like this with a capacitor, with capacitance C, usually variable capacitor works best, and inductor also with inductance L connected to. So in this receiving RCL circuit, you see that there is no power source in this receiving RCL circuit. You only have capacitor and inductor and probably some small amount of resistance due to the resistance of the wires. No wires are perfectly resistive, perfectly conductive. So you want the capacitance and the inductance to be selected in such a way that the resonant frequency of this circuit, which is given by 1 divided by 2 pi times square root of L multiplied by C, you want that resonant frequency exactly to match the frequency of this electromagnetic wave. When you, in other words, usually you adjust the value of the capacitance until that frequency becomes equal to this. And in this case, you have reception. You have induced current in this loop. And once you have, of course, this induced current is very small, and it has to be electronically amplified. And after that, it has to be demodulated in order to have your signal the way you want it. Yes.
So you want the F naught to be equal to that?
Yes, you want F naught to be equal to this F.
Okay. And then that C that's on,
This is the C is the speed of light.
and that's different than the other C, right? That's the other C.
No, it's exactly the same speed of light here and here. It is just the speed of light in air or vacuum. Yes.
So you want the antenna like parallel to the electric.
So you want,
And the loop perpendicular
Yes,
to the magnetic field, and so the loop being perpendicular to the magnetic field creates max flux, so max induced current. What does the electric field do to the antenna?
well, the electric field creates max current in this part.
And it's also induced current then?
Well, it is not exactly induced, it is directly current driven by this electric field. We don't call it induced, but it is going to be current in sync with the induced current created by the magnetic part of the antenna. Okay, other remarks and questions? So this is what we have. Now, you have some homework questions related with this resonance and tuning. You can look at them. And so now the next part of our discussion should be related with the amount of energy that this pattern of electric and magnetic field carries, the amount of energy carried by the electromagnetic wave. And you actually have the information necessary to figure out that amount of energy. Because look, here, if you consider some volume of space like this, some volume of space, you have that the amount of energy per unit volume and let's say amount of electric part of the energy. Well, energy electric per unit volume is given with 1/2 electric permeability of vacuum multiplied by the value of the electric field squared, and by value we mean RMS value of the electric field. So this white part of the electromagnetic wave has this energy density, this many joules per cubic meter. And of course, this is not going to be substantial amount of joules, because epsilon naught is a small number of the order of 10 to the -12 or something of that nature. In a similar, yes.
So what you're saying is that equation helps us find a certain amount of energy in a certain amount of
Of
the
volume.
circuit?
Yeah.
So is it just taking like the side of a circuit or like a length of the circuit?
No, I'm talking about volume in which this electromagnetic wave is propagating. So if you take a snapshot of this volume, the amount of energy that is contained in this volume at this instant is going to be given with, well, it is going to be given with this expression, where E is the instantaneous value of the electric field. Well, if you want to average over time, if you want to average over time the energy that is contained in, let's say, in 5 seconds or so in this volume, you have to take the RMS value. And all questions related with energy of the electromagnetic waves in this chapter require you to think in terms of RMS value of the electric field. In a similar manner, the energy density of the magnetic field, so energy of magnetic field per unit volume, is going to be 1 divided by 2 times magnetic permeability of air or vacuum, mu naught, in denominator, unlike in the case of electric energy, times magnetic field squared, RMS value of the magnetic field again, if you average over time. Yes.
So to find those RMS values, do you just divide the magnetic field by square root of 2?
You divide the amplitude of the magnetic field. So RMS value of anything, let's say RMS value of electric field is amplitude divided by square root of 2, right? Always. And usually, sometimes in the problem, they may not tell you if they're talking about RMS or amplitude. And when they don't say if it is RMS value of the variable or it is amplitude, you usually assume that it is RMS value. But all questions that you are going to encounter in a test, the value is going to be specified if it is RMS or amplitude. Okay, so since the electromagnetic wave contains both electric and magnetic fields, the total energy density, usually denoted with the letter U, lowercase u, is a sum of the electric and magnetic part. In other words, it is 1/2 epsilon naught E RMS squared plus 1/2 mu naught in denominator times magnetic field squared RMS value. Well, epsilon naught is of the order of what we said. 10 to the negative, what was it, 12 or so? And mu naught is 10 to the negative 7 or so. And the question is, in a standard electromagnetic wave, maybe electromagnetic wave emitted by the campus radio station, which one is larger, the electric part or the magnetic part of the energy? What do you think? Well, don't even try to do calculations because you don't know the electric and magnetic fields. But, well, it can be demonstrated that in any standard electromagnetic wave propagating in air or vacuum, the electric part of the energy is exactly equal to the magnetic part of the energy. So there is some kind of a democracy between the electric and magnetic field. So in other words, a standard electromagnetic wave in air or vacuum, you have that 1/2 epsilon naught E squared. I'll skip the RMS because it is valid not only for RMS, but for instantaneous values and for amplitudes also. 1 divided by 2 times mu naught times D squared. So this is valid. It can be demonstrated using the Maxwell equations. You can demonstrate that the electric and magnetic part have to have equal value for the energy that they carry. And from here, look what you're going to get. You can cancel the factor of 1/2, and you can say that electric field squared is equal to 1 divided by epsilon naught mu naught times magnetic field squared. So in a standard electromagnetic wave propagating in air or vacuum, the electric and magnetic fields are with related strengths, related magnitude. Can you tell me what is the value of this expression? 1 divided by epsilon naught times mu naught. Well, epsilon naught is electric permeability, mu naught is magnetic permittivity of vacuum. So those are constants, and those are constants of nature. They describe the electric and magnetic properties of vacuum. So when you have an expression that has two constants, when you calculate it, you're going to get another constant. Can you tell me the numerical value of this other constant? Well, of course, your calculator knows that numerical value, but if you plug in the numbers, you're going to discover that 1 divided by epsilon naught times mu naught is exactly equal to the speed of light in vacuum squared. So this equality that the speed of light is connected with the electric and magnetic phenomena, about 100 years ago, this equality allowed physicists to conclude that most likely visible light is nothing else but electromagnetic wave. Just this fact. And now look, once you take into account that the expression in front of b squared is the speed of light squared, you're going to get E squared is equal to speed of light squared times b squared. And taking square root of both sides, you find that the magnitude of electric field is equal to the magnitude of the magnetic field multiplied by the speed of light for any electromagnetic wave that is propagating in air or vacuum. So this is a useful relation to know. Yes.
So how come the total energy density doesn't just equal?
Yeah. So let's write alternative forms of energy density in a minute.
Okay.
Yes.
So with all those ones that we just wrote, that's the magnitudes of the electric field and magnetic field, not the RMS values.
So here, this equality is valid for RMS values, magnitudes, and also for instantaneous values. At any moment, this length is equal to the speed of light multiplied by the yellow length. Yes.
Does this formula ever lead into like E equals MC squared, or is that an entirely different thing?
Well, everything is connected. Luckily for us, the electromagnetic theory deals with massless objects, luckily for us. So we're not getting complications related with presence of mass. But a little bit later on, you're going to see that energy equals to mass multiplied by speed of light squared is going to appear a little bit later, probably close to the end of the semester. So for the moment, but again, everything is connected. So if you consistently analyze energy from the point of view of relativity and massless objects, you probably can eventually discover this Einstein's formula. For the moment, we're not there yet. Any other remarks and questions? Well, now look, since we have equality of the electric and the magnetic part of the energy density, you can write the energy density of electromagnetic wave only in terms of electric field. For example, you just have to double this, because double this is going to be equal to the whole density. So you can say that density of electromagnetic energy is equal to epsilon naught electric field squared, RMS value, of course. Or you can say that density of electromagnetic energy is 1 divided by mu naught times the magnetic field RMS value squared. So those are three equivalent ways of expressing energy density of the electromagnetic field. And in different questions in the homework assignment, you may have to use one of those three equal expressions.
How can you separate those out when the summation of those two equations equals?
So look, since this is equal to this, instead of writing it this way, you just double this, or you double this. Right? This is the reasoning behind it. Okay, so those formulas allow you to figure out what is the energy that is contained, let's say, in some volume right here, maybe in this room even, right? You just have to know what is the magnitude of the average electric field of the electromagnetic waves that are flying around in this room. And if you know that, just multiply by, square it, multiply by epsilon naught, and you're going to get some small number for the number of joules contained in certain volume filled with electromagnetic waves, like our room is. And some of those electromagnetic waves you see because they're in the optical part of the spectrum, in the visible light part of the spectrum. But many of the electromagnetic waves that are present and flying around the room are not visible because they may be radio waves or cell phone signal, microwave part of the spectrum, microwave cosmic background. So we see only very small part of the spectrum with wavelengths of the order of 500-600 nanometers. Now, next, let's connect electromagnetic waves with intensity of electromagnetic waves. Intensity of electromagnetic waves that are in the visible light part of the spectrum, you call brightness, roughly. So let's connect the brightness, visible and invisible, with electric and magnetic fields of the wave. And look, it is something that you have seen from the analysis of sound waves. So in the case of sound waves, we define intensity of the wave as energy that these waves carry per unit time, t, per unit area perpendicular to the direction of propagation of the wave. Exactly the same definition is the definition for intensity of electromagnetic waves, light or radio waves or any other part of the electromagnetic spectrum. So now the energy per unit time, is also power. So you get power per unit area. Now, let's see how to express this intensity in terms of electric or magnetic vectors, electric or magnetic fields. And look, it is not that difficult. Just think about the area that you want. Let's say here is some area perpendicular to the direction of propagation of the electromagnetic waves. Here is this area, A. And, well, think about some time interval t. In time interval t, how much energy is going to cross this area is the question. And look, all electric and magnetic fields that are going to cross this area in time t, all those electric and magnetic fields are going to fill a box like this. A box like this is going to be filled. So the area here is this area that we started with, and this length of the side of the box is exactly equal to the speed of light multiplied by the time t during which you're doing the observation. So the amount of energy that crossed this side of the box is equal to the amount of energy that is contained in the volume of this box. And we can calculate it. So we're going to get the intensity of the electromagnetic wave is the energy contained in the box. And that energy contained in the box is going to be energy density multiplied by the volume of the box. But the volume of the box is the area A multiplied by the length of the side CT. So all of this has to be divided according to the definition to the time interval T and to the area. The time interval cancels, the area cancels, and for the intensity of the electromagnetic wave, you get it is just equal to energy density multiplied by the speed of light. And this is the result that you need. The energy density, again, can be expressed in terms of RMS value of the electric field or RMS value of the magnetic field, like in the formula that we derived. Let's see questions and remarks. So now you have given the electric field, you can immediately calculate the density. Or given the magnetic field value of the electromagnetic wave, you again can calculate density, or vice versa. Given the intensity, you can figure out what is the RMS value of the electric or the magnetic field. And this formula again is needed for some homework questions. Let me see if problem 16 maybe. Let me see what is problem 16.
So the top equation is just like a slice, and the bottom equation is like a box.
Yeah, well, so say it again.
So the top equation is just for like.
So this equation is the definition for intensity, for brightness of electromagnetic wave. And this equation says intensity is the energy that crosses area A, perpendicular to direction of propagation, per unit time. This is what the definition says. And I expressed the energy in nominator as the energy that is contained within some box with certain dimensions. And everything else canceled out, and you got that the intensity of the electromagnetic wave is the energy density multiplied by the speed of light. Simple result, yes. Yeah, your question? No? Okay, are there any questions on the internet? Okay. So let me see a homework problem as an example. Okay, let's do problem number 16 from the homework assignment on chapter 24. It is about the cell phone. Let's see what they're asking there. So problem 16 from the homework assignment. So problem 16 from the homework assignment is saying that you have electromagnetic waves from a cell phone to a cell phone. And they say that the RMS value of the electromagnetic wave that comes from the tower into your cell phone is this number, 1.6 times 10 to the negative 10 Tesla. This is the magnetic field. That wave passes through an open window with given area. We're going to assume that this open window is perpendicular to the direction from which the wave comes, perpendicular to the direction from the cell phone tower. And they're asking you how much energy does this wave carry through the window in 45 seconds phone call. So how much energy comes through the window that is perpendicular to the direction from the cell phone tower in 45 seconds. Oh, look, since energy is related with intensity like this, energy divided by time and divided by area, I guess, they give you the area. They give you the time interval. For me, it is 45 seconds. They don't tell you what is the intensity of this electromagnetic wave directly. But you know that the intensity of the electromagnetic wave is energy density multiplied by the speed of light, which can be expressed as 1 divided by mu naught times B RMS squared times the speed of light. They give you the magnetic field RMS value. So just multiply it by the speed of light, divide by magnetic permeability of air or vacuum, and you're going to get your intensity. In other words, S is known, time is known, area is known, figure out energy. So energy that comes to this window in 45 seconds is going to be intensity times time times area. In other words, it is going to be 1 divided by mu naught times B RMS squared times C, the speed of light, times the time interval multiplied by the area. And this should be the value of energy that they are asking. In SI units, that energy is going to be in joules. And you see that this amount of energy is very small. It is of the order of 50 millionth of a joule, not that large amount of energy. Okay. Now, comments, remarks? If not, let's talk about polarization of light. We mentioned something like this in one of the previous classes. Now let's specify it a little bit more. So look, the electromagnetic wave that is shown on the board has a direction or directions in space that are preferred. For example, the electric field oscillates in vertical direction, back and forth in vertical direction. So this is a preferred direction in space. The magnetic field oscillates in direction perpendicular to the board, like this. So those are directions that are preferred directions. We say that this particular electromagnetic wave is polarized, and the direction of polarization, or so-called polarization axis, is the direction of oscillations of the electric field. In our case, the polarization axis is this vertical axis, And in a diagram, the direction of polarization usually is shown either with a square or a circle, and in that square or a circle, you're shown the axis of polarization, in this case, this axis right here. Or if you use the circular notations, this is the direction of polarization of the electromagnetic wave that is created, that is shown in a graphic form on the board. Now, electromagnetic waves that we encounter, electromagnetic waves that are from natural sources, are not polarized. This means that at one instant, the electromagnetic wave has electric field that is oscillating this way, and the next instant it is going to be oscillating maybe this way or this way, a little bit later oscillating this way. In other words, for a finite time interval, you pretty much have all directions of oscillations of the electric field present. Just keep in mind that those directions of oscillations have to be perpendicular to the direction of propagation of the electromagnetic wave, right? Electric field always perpendicular to the direction of propagation. Why does this happen? Because ordinary light sources emit, individual atoms from them emit light for short time interval. So the fluorescent light that is on the ceiling here, one atom at some very short time interval emits electromagnetic waves that oscillate this way. But the neighboring atom doesn't know about the first atom, and it may emit light that is oscillating in completely different random direction. The result is light, electromagnetic wave, that is oscillating in all possible directions, perpendicular again to the direction of propagation of the light. Now, if you have unpolarized light, and if you pass that light through a filter, which is a transparent, semi-transparent filter of this type, it is just like the lenses of sunglasses, polarized sunglasses. So the material here is long polymer molecules that in the process of manufacturing have been oriented in some particular direction mostly. Let's say direction like this. So this particular plastic filter is going to take, well, the light that comes in, unpolarized light, oscillating in all possible directions. But the filter is going to have the property that it is going to absorb the light component that is oscillating in some other directions and only let through the light component that is oscillating, let's say, in vertical direction. Just because the molecules of the filters have been arranged that way. As a result, unpolarized light coming in on the other side is going to come out and is going to be polarized along the axis determined by the polarization filter. Of course, the light that makes it through is going to be polarized, but its intensity is going to be reduced. And you can demonstrate with a little bit of trigonometry that the intensity of light is going to be reduced by a factor of 2. So unpolarized light with intensity S comes in. Polarized light is going to get out with intensity S divided by 2. Okay, so now let's use a light source. Oh, we're out of time. But next time, we're going to polarize the light with one polarizer. And after that, a second polarizer is going to analyze this polarized light. And we're going to see how the intensity of the light that goes to those two filters is going to be. That intensity is going to be given by a simple equation called Malus' law. And where most of the homework questions at the end of the assignment are related with this simple formula. We're going to talk about Malus' law next time. And next time, we're going to, I hope, we're going to be able to finish the homework questions that you may have. And we're going to start chapter 25, which is the first chapter of optics. So we're going to talk about reflection, refraction, lenses, and microscopes, telescopes, and so on. So this is coming. Questions and remarks about what we said so far? If not, see you on Friday.